So we're going to take a little bit of time here to go over the equilibrium handout that you have been given, titled Equilibrium 1. So we're going to go through a set of problems, hopefully to help you review concepts if you've learned in equilibrium in Unit 9. So 1A says, given calculate Kc at 303 Kelvin for SO2 plus Cl2 going to SO2 Cl2. If Kp is 34.5 at this temperature. So this is a classic situation where you're going to have to use that conversion equation. So it says Kp is equal to Kc times RT times delta N. So remembering that R is the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. T has to be in the absolute scale, so it has to be in Kelvin. And delta N is the change in the number of moles of gas from products to reactants. So in this particular case, we are given Kp, we have R, we have T, and we obviously have delta N because that is the equation that we're looking for. So we're just going to rewrite it to solve for Kp. So we put in our value for Kp that's given is 34.5. R is 0.08206. Again, units are meaningless with these types of calculations. As long as the temperature is in the absolute scale, you're fine. T is going to be 303 Kelvin. Delta N, so it's the number of moles of product, 1. Take away the number of moles of reactant, 2. So 1 take away 2 is -1. You perform this calculation and you get 858. So the equilibrium constant for this particular scenario would be 858 for Kc compared to 34.5 for the value of Kp. So for part B, this is part A, so for part B, it says given that there are 10 atmospheres of SO2Cl2 present in equilibrium, determine the partial pressures of SO2 and Cl2. The flask volume is 50 milliliters if at all needed. So we're going to want to use our ice box. You're going to want to use your ice box here, so just write your equation over it. Sometimes it's useful to do a double line separating reactants from products. So once you have your ice box done, it's time to start putting things in that you have. So the only thing that we really have for this problem is that we know that there are 10 moles of 10 atmospheres of SO2 Cl2. So and that is at equilibrium. So the only thing that we really can say is that we had, let's assume we start it from 0 because we really don't have any other information. And we know then that plus 10 must have been what was formed. We don't know what we start it with. We do know the stoichiometry for the equation is 1 to 1 to 1. So we must have lost 10 atmospheres of pressure from both of those. So I have x minus 10, x minus 10, filling in the lines. We write our equilibrium expression, Kp is equal to the partial pressure of SO2Cl2 over the partial pressure of SO2 times partial pressure of Cl2. And I know that this is equal to 34.5 in the equation. So I plug in my values for Kp. Kp is equal to 34.5 is equal to 10 over x minus 10, x minus 10. We're just going to skip a few steps. We're just going to rearrange this as we've done before into our quadratic form. So 34.5x squared minus 690x plus 3440 equals 0. So basically, to get that, you're going to multiply. You're going to expand these two factors, multiply this entire denominator by 34.5, and then subtract 10 away. When you are done, you're going to plug that into the quadratic equation and solve for your roots. We get two roots, 9.461, and the second root is 10.5. So we look at the situation that we have. X could not be 9.461 because then you would end up with a negative number for the starting concentration, so it must be 10.54. So the partial pressure of SO2 is equal to the partial pressure of Cl2, and that is equal to 0.54 atmospheres. So again, you're just plugging in the 10.54 in for x. 10.54 take away 10 is 0.54, which is where that number is coming from. So again, this would be at equilibrium. And the final part of this question is, what is the total pressure of the flask at equilibrium? Well, you're just going to add it all up. So for part C, P total is equal to the P of SO2 plus the P of Cl2 plus the P of SO2 Cl2. See, it's kind of crowded here in the bottom. And we simply add those up at equilibrium. So we have 0.54 plus 0.54 plus 10 is equal to 11.08 atmospheres. And that would be the total pressure. Again, make sure that you look, when you solve for your x, make sure you know that you're just going to substitute it into your equilibrium line and then solve. And then because it's total pressure, we're looking at Dalton's law of total pressures, so we're just going to be adding up the pressure of each species that is present at solution. So now we move on to question 2, which simply is a little bit of theory. It says consider the equilibrium of Na2O solid plus sulfur dioxide giving Na2SO3 or sodium sulfite. So it says write the equilibrium and constant expression for the terms of partial pressures. So Kp for A is equal to the products over the reactants. So the first thing we got to notice is that we have solid and solid. So we have no product that we're going to write, so we're just going to put a 1. And then over the reactants, which is the partial pressure of SO2 raised to its coefficient, which is 1. So that's all we have to do for A, is 1 over the partial pressure of SO2. And part B, then again, we're just going to look at that exact explanation. It says, why doesn't the concentration of Na2O appear in the equilibrium constant? Well, it is solid, is the answer. And the concentration of a solid doesn't change appreciably. So it is excluded. And that's the only reason we don't write it. It's also true for pure liquids as well. So for question 3, it says that methanol is produced commercially by the catalyzed reaction of carbon monoxide and hydrogen. And CO plus 2H2 gives me methanol. An equilibrium mixture in a 2-liter vessel is found to contain 0.0406 moles of methanol, 0.17 moles of carbon monoxide, and 0.302 moles of hydrogen gas at 500 Kelvin. Calculate the Kc at this expression. First of all, we need to make sure that we emphasize the fact that it's catalyzed is irrelevant with equilibrium. Equilibrium will simply be achieved faster, but it will not affect where equilibrium is. So the fact that they're mentioning that it's a catalyst does not change anything at all. So we write the equilibrium expression. They are all gases, but it's asking for Kc. So Kc is equal to the concentration of the products raised to its coefficient over the concentration of the reactants. Now, we got to be careful because we do have that 2-liter vessel that we've got to take into consideration. So we have moles listed, and then we have the volume that they're contained in. So we're dealing with concentration, so that does matter. So we have 0.0406 moles in a 2-liter flask, all over 0.170 moles over 2 liters for carbon monoxide, and then 0.302 moles 2 liters squared. So we go through and we will do the arithmetic, and we'll find that it is 10.5 is the answer. So just make sure that you do your division, take your volume into consideration. By doing that, don't forget your square. Make sure that you get that's on the denominator, and you should get an answer of 10.5. The next question is a fairly good question for a lot of reasons. I've used it several times on assessments. Just basically this equilibrium process. But it says phosphorus trichloride gas and chlorine gas react to form phosphorus pentachloride gas. So the first thing we're going to do is we're going to write the balanced equation for this particular reaction. So phosphorus trichloride gas plus chlorine gas. Remember that chlorine is a diatomic molecule. That's one little thing that causes a problem sometimes and gives me phosphorus pentachloride gas. So write the balanced equation. It should all be 1-to-1. It should be good. So next up, it says a gas vessel is charged with a mixture of phosphorus trichloride and chlorine gas, which is allowed to equilibrate at 450 Kelvin. So that is a very important line. So they're saying that the equilibrium line, concentrations are given. So they're asking for Kp. So that makes our life a lot easier since that is at equilibrium. So Kp is the partial pressure of there's our equilibrium expression for partial pressures. We're going to plug in our values. So pentachloride is 1.30 atmospheres. Cl 0.157 and 0.124. And that comes to 66.8. And there's our answer. So again, because it's at equilibrium, we just write the expression and fill it in. For part C of this, it says, does the reaction favor the reactants or the products? Well, remember what we had talked about earlier. If KEQ, or the equilibrium constant, is greater than 1, it favors products. Basically meaning that the numerator on the the expression would be greater than the denominator. Since the numerator is the products, that means that products are in greater quantity, so we say that the reaction favors products. So we move on to question 5, which is sort of a little bit of a theory. It says explain why partial pressures of gases can be used in place of concentrations in an equilibrium expression. So first of all, the concentration of a compound is equal to the number of moles over the volume. So basically, we know that we have the ideal gas equation, and we have N, and we have V. So we can simply rewrite N over V is equal to P over RT. Now, this and this are constant values. So basically, we can see that concentration, moles over volume, is directly related to pressure. As this side would go up, so would the pressure have to, assuming the temperature is being held constant, which we have to. So the only real explanation that we need here is that we can see that as N over V, which is moles per liter in this case, goes up, so must the partial pressure as well. So they're directly related, but unfortunately they're not exactly the same. And we can see the RT, and we know that expression that we've used earlier has RT in it, and that again is wise, so we can actually convert between the two. So now we're going to look at a situation where we have masses given, and we need to convert to moles. Use those moles to try and figure out exactly what the equilibrium constant is. So the first thing we're going to do is just do those conversions. So I have 1.374 grams of H2, and we're going to convert that into moles. So that's equal to 0.680 moles. Bromine, same thing. And the formula weight of bromine is 159.8. And that's going to give me 0.440 moles. And at equilibrium, I'm at 0.566. So I'm just going to continue to convert these. And that's going to give me 0.280 moles. We do have this whole situation here where we are looking at a 2-liter vessel. So these all need to be converted for 2 liters. So we're just essentially dividing them by 2. These are moles per liter. Now, although in this case it's really not that necessary to use the icebox, because you probably can figure out what each quantity is based on the information you're given, but it really does help organize the data. So we have H2 is 0.340, bromine 2 is 0.22, then we assume that we have none of that to start with, and we know at the end of the reaction we have 0.140. So now it's just a matter of trying to figure out exactly what has happened. So this plus the change line has to equal that. So we know that it's got to be negative 0.2. It's the only way that would work. Since these have the same coefficients, that would of course be the same. So this plus this gives me 0.02. And then finally, HBr would simply, because of the 2, would gain, it's a product, would gain twice that. So 0.40. course, giving me 0.40. So there's our equilibrium concentrations of H2, Br2, and HBr. Next up, the question is asking us to determine what the Kc value would be. So for part B, Kc is equal to the concentration of HBr squared plug those in. 0.4 squared divided by 0.14, and I get 57.1. And there's our answer. That's our equilibrium expression constant. So for question 7, you will see that we have 2 moles of SO2 plus 1 mole of oxygen producing 1 mole of sulfur trioxide. First of all, we should have a little look at this, making sure that we are balanced. This is 2 moles of sulfur, and I have 1. So I probably need to put a 2 in there. That will affect results when looking at the actual equation. It says in an equilibrium mixture, the partial pressure of SO2 and O2 are 1.135 and 0.44 atmospheres, respectively. What is the equilibrium partial pressure of SO3? Well, they gave us Kp, so let's write out the partial pressure of SO3. So we're simply just going to write it out, making sure that we square the appropriate values here. So we know a 0.345 we don't know what that is, but we do know the partial pressure of SO2, sorry, is 0.135 squared 0.455 as well. So we can go through this calculation pretty straightforward. 0.135 squared times 0.455. So 0.345 is equal to the partial pressure. Now we can just basically multiply this answer with 0.345. And to get rid of the square, we're just going to take the root of it. Is 0.0535. So just we'll report it. The partial pressure of SO3 must be equal to 0.0535 atmospheres. And there's our answer. So when you do get that answer, you can actually just plug it right back in to Kp and make sure that you are going to get the correct answer. And you'll see that when you do it for this one, that you do actually get the correct answer. Normally, if this equation was not balanced, I would not have put a 2 here, but just something always that we should be checking. So we'll go down to number 8, which is the last one. So it says at 800 Kelvin, the equilibrium constant for I2 to 2I is 3.1 times 10 to the negative 5. If an equilibrium mixture in a 10-liter vessel has of containing 2.67 times 10 to the negative 2 grams of I gas, how many grams of I2 are in the mixture? So let's look at A first. Once again, you can see in part B as well, it's not balanced for some reason. Anyway, 0.0267. So the first thing we should probably do is get that into moles. And the molar mass is 126.9. That's going to give you 2.1 times 10 to the negative 4 moles of I. Concentration of I is equal to the number of moles divided by the volume. So 2.1 times 10 to the negative 5 moles per liter. So we write out our equilibrium expression for this. It is Kc, we always double check, is equal to the concentration of I squared over the concentration of I2. So we have I and we have Kc. So I2 is equal to the concentration of I squared over Kc. Kc's one. Concentration of I2, I'm simply just running through and solving for it, is 1.4 times 10 to the negative 5 moles per liter. The question is actually asking us for grams, so we have to take that into account. 1.4 times 10 to the negative 5 moles per liter times 10 liters times 253.8 grams per mole and 3.55. And that gives me my answer for part A. So we're going to have a little look at B, and you'll notice that once again, the equation, it wasn't balanced in the question, but it is balanced down here. The concept here is very, very similar to what we just did. It says for this reaction, Kp is equal to 3.0 times 10 to the 4 at 700 Kelvin. In a 2-liter vessel, the equilibrium mixture contains 1.17 grams of sulfur trioxide, 0.105 grams of oxygen, and how many grams of SO2 are in the vessel. So the easiest probably thing to do is to actually convert Kp to Kc. So Kp is equal to Kc times RT delta N. So we can start with this particular question, with this particular part. So Kc is equal to Kp over RT delta N. Kp is 3.0 times 10 to the 4 R And we now just need to solve for our delta N. So we're going to go from 2 moles to, so we're going to go from 3 moles, 2 moles of SO2 and 1 mole of O2 to 2 moles of SO3. So we're going to have a negative 1. So we solve, we're going to have to solve that particular equation. We'll do this in steps. So 0.08206 times 700 Kelvin to negative 1. So 3 exponent 4. So your Kp value is 1.72 times 10 to the 6. Obviously, equilibrium lies very much towards the product side of this. And again, that is your Kc value that you're going to use. So the next thing is we have grams. So 1.17 grams of SO3. So we got to convert this to moles, just like we've done a little bit earlier. We have, I think, 80 grams per mole. So 1.17 divided by 80 equals 0.01462 moles, and 0.105 grams of O2 0.00328 moles. It is in a 2-liter flask, so we divide both by 2 liters. So we have those calculations done in moles per liter. I'll throw the big M after them. Now, once again, we have to write the equilibrium expression. SO3 so we have the equilibrium expression now. So now we're just going to plug in our values that we have. The question is asking for us to solve for SO2. So we are after this variable. So we can write the concentration of SO2 is equal to the concentration of SO3 squared times Kc times the concentration of O2, and take the root of the whole thing to take rid of the square. So SO3 has 7.31 times 10 to the negative 3 moles. We're going to square that. And we have the concentration of oxygen listed there. So the concentration of SO2 is equal 7.31 exponent 3 negative squared divided by 1.726 is equal to the root of 1.89. Take the root of it. So again, this would be in moles per liter. So we're looking for grams. So 1.376 times 10 to the negative 4 moles per liter times 2 liters times 64 grams per mole. This is all for SO2. So times 2 times 64 equals 0.0176 grams of SO2. And that is our final answer. Again, normally you would not have to worry about that a balancing equation, but it is always something good that you should check.